The Fathom one, the one that says Mark's Fathom Note Taker. Unsurprisingly, that one's mine.
Got it.
But yeah. Hey, Nidhi, how's it going?
I should try one of these. I never tried them. Does it work well?
I thought it would be like good enough or something. Okay, it's better than nothing. Fathom is incredible. I don't know about Otter Pilot. I've never actually heard of Otter Pilot. I know Otter, but and I don't know about Read AI. But Fathom is incredible. I actually would highly recommend. And I have a referral code if anybody wants it.
I will try. Phantom. I'm taking a note for myself. Hey, everybody.
Hey, friends. And Mert, you're going to the dinner tonight, right?
Yes.
Nice.
What a good day.
Yeah, this will be great. And Nidhi will be there as well.
Hi, Nidhi. Thanks for your ping. I appreciate it.
Hey, Mert. Super excited to hear your talk today.
Awesome. Mark, you give me the light.
Yeah, we'll let people come in. Nobody's. If any of us took any of the Google culture in, then we are not on time to meetings.
The worst parts of Google culture.
Yeah.
I'm kidding. Hey, anyone recognize my background?
Morro Bay?
Yes, Mark. Sorry, yeah. I don't think it captures, but this rock right in front of Morro Bay, and it's a very small town. It just so like it looks so cool to me. Like you should pass by if you're driving in south from here one day and take a look at it. I love it.
It is absolutely incredible, and I did a triathlon there a couple years ago. That's how I know it. And like you start and end every part of the triathlon at the rock, and so like the swim is close, but then like you bike 25 miles, and you're just going towards the rock for like an hour and a half, and it's never getting any closer. It's just it's huge and really.
It's funny. Do you see the buoys on the picture?
Yeah.
I took this picture Sunday because I did a triathlon there.
Oh, you did? You did the Ironman, a half Ironman?
Yeah, I did Morro Bay half Ironman.
Amazing. Did you finish the swim?
I did. I got lucky and also a little bit on the strong side of the swim. So I started second wave. Okay, so great. What happened to me was like when I got out of the water, I was like 30% slower, right? Like I had a time in my gap, and I know I wasn't like my best fitness, blah, blah, but I'm like, oh my God, I sucked at swim. So I didn't realize it, I will say. Yeah. But then I heard it got worse and worse afterwards. And of course, worse means like the people who are expected to swim slower, they start late and they got hit by the stronger currents. And it just like, I think they stopped like 300, 400 people off the water. So
yeah, so for people who aren't weirdly tapped into the triathlon circuit of Sanford, like California.
Sorry, yeah.
No, one of my friend's dads just did it as well. He also.
Oh, really?
Yeah, and but yeah, no. So for people who aren't into triathlon, I grew up swimming. I grew up in Hawaii, so like water is great for me. But most people who do triathlons are big runners or big bikers. And so everybody says, you just get through the swim and it sucks, and then you're fine, and then you get to the fun stuff. And I resent that because I love the swimming. But everybody, like most people, are like intimidated by the swim. So this event last weekend was really tough because the timing was just they didn't think about it properly with the tides. So the tide was coming in at the wrong time. So a lot, like basically the swim ended up being like 2.5 times as long as it should have been because the water was moving against them. And you also have a time limit. Like they don't just give you endless amounts of time to swim because they don't want people to die. And so so they cut off a lot of people and like brought them back in. Also, the water was like 54 degrees Fahrenheit, so it's really cold. And so yeah, 350 people got disqualified because of this timing and cold water and stuff. It was just crazy. So congratulations, Matt. That was very.
Yeah, I'm still high from it. So I don't need coffee this morning, but I.
Great work. Well, cool. I guess before we actually get started, I want to get really one quick piece of like feedback. Just how we organize these event types of things. Like I'm messaging it on the WhatsApp and putting out little polls and stuff. Is that like, do people feel like that works well for them? Like, do you feel like you see those events and you see the polls and that works, or like it's chaotic and you miss things? Evan's like, yeah, it's a little chaotic, but it works. Okay. Well, don't worry about unmuting and stuff if you want to, but if anybody has feedback or any suggestions, definitely let me know. Continuously iterating on this. And then yeah, the other thing I'll say, we have our next climate dinner. If you're in the Bay Area, we have the next Xoogler dinner tonight. If anybody wants to try to get in there last minute, let us know. Nidhi was awesome and ordered the food for us already, but we can add people if last minute people want to join. But for future ones, yeah, we'll be doing it again either in early June or in early July. I'm gone for a lot of June, so might be early for the next one. But stay tuned, and yeah, without further ado, take it away, expert Mert. I'm really excited to hear more about this.
Oh no. Thank you, Mark. First of all, again, thanks, Mark, for scheduling this, getting in touch with me, and your interest. He also introduced me a couple of people and investors. So, Mark, I really appreciated what you're doing with the group, and all of you guys. Nice to meet you. A few disclaimers. I'm gonna use an existing deck. I changed it a little bit based on this. So it's of course our investment pitching deck, but I'm not trying to do that right now. I will try to focus on the technology or plastic recycling. But if you hear me getting into the kind of pitch mode, I apologize for that. It's not my intention, but I have been pitching for the last 4 months, so it just probably becomes naturally. So, but I'm not trying to pitch the company to you guys. So, but also I'm super excited about, of course, our company. So it will be kind of natural. So what I will try to share my entire screen, try to see you guys on the side. But if the slides are too small, let me know. Let's see. Okay, maybe, yeah, I don't need to see you guys. I think I can make this bigger. Or is this size okay, Mark or anyone? For now, okay. All right.
Yeah, I mean, if you can go into presentation mode, not a bad thing, but
okay, let me do it. Let me do it. Okay, sounds good. And we have 52 minutes, right, Mark? Like
yeah.
an hour. Okay. All right. Yeah. So my company, Rhea's Factory. But let me just starting with my story a little bit. My co-founder is on the left-hand side, Arzu. She's the scientist, biomolecular scientist. Her story is also fascinating, but we can talk about that maybe during the dinner. I worked at Google for 9.5 years. First 6 years, it was so much fun. I enjoyed it like tremendously. I was part of the Google Assistant team from day zero. I clearly remember they formed a team right after Amazon launched Alexa devices, and it was like, and I was a part of the search team. And then they formed this smaller group within search to tackle this whole Amazon Alexa situation. It was so much fun, very small team. It was almost like a small startup without any financial constraints within Google and Google's amazing culture. And then I was a TPM, PM program manager at the time. And then a couple of years later, I became a product manager. I stayed at Google Assistant team. I shipped, products and hardware products, software features, and all that stuff. And as everything changes, I change. Google started to change, as we now much more clearly see it. Google Assistant team started to change, and I moved in different teams within Google, mainly looking for something for my personal growth, but also I'm like an engineer by education. I'm a nerd. I like technology a lot. However, during that time, I also started to realize that, okay, technology is not always for the benefit of humans and society and planet. So anyways, that was kind of lingering back of my mind. I worked at YouTube for a year. That was kind of an interesting time because I had two kids. I have two kids, and I work at my day job, YouTube, come home, see them watching YouTube, and then I stop them. Hey guys, don't watch YouTube anymore, blah blah. And then they're like, Dad, aren't you working at YouTube? Like, what's going on here? I'm like, okay, there's something that I think I need to think about my life. And then last, I moved to Fitbit team. I'm into triathlons, as you can tell, also fitness, etc. So Fitbit team sounded like a good fit at the time. And a year into it, I was impacted in 2023 January layoff in a very unique situation because I was working on a hardware product, fitness trackers, not the watch, but Fitbit's charge line that's supposed to be launching in 2023 October. But Fitbit team got impacted with the layoff significantly. And basically I was told, hey, you will be laid off in October. So they gave me like 9 months because they want me to ship the product. And of course I could move within the Google team, etc., etc. Long story short, in January, I'm like, okay, I was already soul searching what I want to do, etc., etc. So within like 3 to 6 months, I feel now lucky. Of course, I was giving the time. I decided that two things. I decided that I want to do my own thing. Second one was I want to do something meaningful. Using technology. My first experiment with that was co-founding another startup with another co-founder who had a research in machine learning algorithms to be used for cancer diagnosis. And the co-founding relationship didn't work well, so we stopped that. And then during that time, though, I was exposed to learning more about not just large language models, which I kind of knew. I was doing a 20% project at the time at Google too, but the transformer architecture of LLMs being used for protein engineering. In very short, if probably you are maybe familiar, but proteins are amino acids. Amino acids, there are only 20 amino acids in a chain. However many amino acids come together, they become a 3D structure, protein, and then proteins do amazing things. They have different functions. So that was fascinating to me, and I'm like, oh my God, however this ChatGPTs of the world is distracting our daily lives, protein engineering world is being disrupted too. And I was super excited about it. That's when I met Arzu, who basically created the vision of Rhea's factory at the time before I joined her, which I did beginning of this year, and it's two of us trying to make this vision come true. What is that? What we are trying to do? We are trying to basically develop proteins, enzymes that can break down plastic in a very sustainable way to its raw materials. But so what's going on? I mean, I know you guys all know about the plastic problem. I knew it too. But really, when I start digging into this, like the sheer problem that we are facing or ignoring is like mind-boggling to me. The amount of plastic that was produced, almost 10 billion tons, and half of it was last 4 or 5 years, and it's just accelerating. And unfortunately, almost 90% of it is either landfill or burned, basically. And landfilling is also becoming a problem because there is no more land. I mean, China, etc. People, some places are not taking plastic garbage waste anymore, or they are charging it, etc. Needless to say, you are hearing maybe more and more, but maybe I am biased or paying more attention to it, but this whole microplastic issue found everywhere now, not just in oceans, but in our bodies and everything. Because even though we try to put them in a landfill or incinerated, these plastics they are leaking into the environment. So I am assuming there is no like description of the problem statement, but it is huge. But if we can get into more about the recycling part, like what is happening, why this recycling is really a problem. There are multiple breaking points. One of them is it's this end plastic products right here. There are multiple different types of plastics, and even within a plastic bottle, there are almost like 3 different types of plastics. So the current technology is not being able to recycle them in quote, because right now we are not really recycling them. But anyways, these 3 different plastics, or assume that you put your plastics in a blue bin in your home, they come to collection, and then they need to be sorted to different types of plastic to be eligible for certain recycling options that we have, which I will talk about. But not, so one problem is sorting, right? And if you think about it, in California, actually, we are trying to do a really good job. We have different bins. If you think about the whole world, right, part of the world, this is not happening at all, versus some people in Belgium, maybe in France, doing even better than us. So there's this whole spectrum of collection and sorting issue. After that, even though sometimes you can sort, let's say, plastic type 1, plastic type 2, I will talk about that. But then you also need to have recycling processes for each type of plastic, which we also don't have. And the third problem is some of the plastic end products are mixed layers, like goldfish snack plastic. They are calling poly-coated paper, meaning paper. Even my to-go cups, right? They are paper, but to be able to hold the liquid, they have a tiny bit plastic layer in it. So it's a mixed layer product. So how can I recycle this material, right? It has paper, it has plastic, it can have multiple different types of plastic, etc., etc. So these are like the really big bottlenecks of the current recycling methods. When I say methods, the main one, the scaled one, which is also like really low, 8%, is the mechanical recycling. And it is not recycling, it's downcycling actually. Because what it does is, it tries to collect one type of plastic, usually out of 7, maybe multiple of them are eligible for this. They collect them, sort them, and then, okay, they make sure there's only one type of plastic. After that, they melt them, they crash them and melt them, and they become like a pebbles. And then they use them for molding for a different type of product. During this process, though, because of melting, the characteristics of the plastic degrades. So let's say you have a to-go box for your food, so it's a food-grade plastic, can never become, again, food-grade plastic with this mechanical recycling. The other problem is you collected, you sorted one type of plastic, but the colors can be different, etc. So when you go through mechanical recycling, they become a weird color. So you cannot even, again, use them for certain type of recycled material, for example. So that's the mechanical recycling, which is the most, when people talk about plastic recycling, they usually refer to mechanical recycling, which is not recycling. And I will come to the second one. But before that, I have been talking about like these different type of plastics. So on the left-hand side, you can see, at least in our plastic materials, they need to put these scale from 1 to 7. And actually, it is a little bit ranked towards how eligible they are for recycling. And on the left-hand side, PET and the high-density polyethylene, and number 2 and number 4, PE, combine them. PET and PE are like the most common plastic types that being used. The interesting thing is, which I learned really later, you can see this logo for type of plastic looks like a recycling logo, which is not. It doesn't mean they can be recycled, which was like crazy to me. And I put the right-hand side on the recycling logo, which is exactly almost the same, but it is not. So that's, I think, like a really, in my opinion, playing with the, consumers' perception. I do. Sorry. You guys see my slide, right? Okay, I'm coming back. Was there? Well, if you want to ask a question, stop me, please.
Yeah. Sorry, I didn't ask if you wanted us to raise hands or ask questions at the end or what.
Jump in. Don't worry. Cut me off. Yeah.
I wanted to ask, is this an international division, like the 1 through 7? Is that internationally standardized?
Yes.
Okay, cool. And then
I'm not sure if every country is following it, but I think US, Europe, couple like different alliances are doing it.
Cool. And then in terms of like human health, do you know which ones are like better or worse for you? Like, leak more forever chemicals and stuff like that into the food?
Yeah, I don't know. That's a really good question. Probably my co-founder would know, but I don't know. Yeah.
I mean, it's not your focus. No worries. But, okay, cool.
I should learn everything about plastic. It's fascinating, but that's a great question, Mark. Anything else, folks, or should I continue? Okay.
I have a
quick question, Mert. First of all, I noticed that you're talking a lot about plastic specifically. Is there a reason why, and maybe this is just a macro question, why your company is focusing specifically on polymers, not other types of recycled materials?
You mean other than plastic?
Yeah, because there's a lot of other materials,
Yeah.
obviously, that could be recycled. And I'm just curious why. Obviously, we know
Mhm.
plastics is bad, but there are other. Is most of this presentation focused exclusively on polymers?
Yes.
Okay.
Yes, and that's our focus too. That's a good question. Why? Maybe multiple reasons. One is my co-founder is coming from an enzymology or biomolecular science. What happened last maybe a decade ago or some time frame like that, there was a bacteria found in Japan, actually near a plastic recycling facility, in a waste part of the recycling facility, and they observed that this bacteria was basically eating, if I call it that way, plastic. So that was the first time humans found that an enzyme can break down plastic. So that's opened up this whole area of, okay, I mean, it is super slow, it's not effective, of course, but nature has this kind of protein and enzyme that can do this. So that opened up this space. And since then, it has been a lot of research and improvement of these enzymes. So that's how we come to a point where we know, at least for PET, we have an enzyme in the wild, which is called wild type enzyme, that can degrade PET. And there have been companies and universities working to improve this enzyme to make it more, industry-wise, scalable, and etc. What I'm trying to answer to your question is, we are realizing that there is this I'm going to call technology, but enzyme approach, and I think the opportunity is so much, and it can fix this plastic recycling problem in a very sustainable way. And with the LLMs of the world impacting protein engineering, two of us basically said, hey, let's focus on using these two technologies to improve and also like take to the next level of using enzymes for plastic recycling. Maybe in the future of Rhea's factory, we may go to another field, I don't know. But even within this field, the opportunity/work is tremendous. So some personal level, some historical level, some about where technology is, maybe the short answer. Any other question? Okay, so the other part I want to mention before I get into our process is here I mentioned only chemical recycling, but maybe if you're interested, you are hearing either chemical recycling or advanced recycling, which is also relatively new. And these processes are developed by petrochemical companies. But by the way, I didn't go over this value chain here, but just like you're familiar, it starts with oil. Actually, it starts with kind of like not the high quality of oil. The resin manufacturers create monomers becomes polymers and all that stuff. And like I tried to explain, plastic product, blah, blah. So the one key here is it is really cheap to create plastic from oil. And this is basically done by big oil companies or like really big petrochemical companies. So these companies are very familiar with, of course, chemical processes and industries. So they realize the limitations of mechanical recycling, not only from an environmental perspective, but also from economic perspective. And it's not like I said, it's downcycling, it's not recycling. Long story short, for the last couple of years, they have been working on this chemical recycling approach, which is more successful in the sense that it can bring certain type of plastic back to almost oil. So from a recycling material perspective, it has advantages over mechanical recycling. And since these companies are familiar with chemical processes, they have found different ways to do that. The downside is that these processes require very high temperatures, like 500, 600 centigrades and Celsius, etc. And they do give out like poisonous gases in certain conditions, and they are still struggling to scale that too. So even though we are basically, when I say, but the reason I'm mentioning about these petrochemical companies, they're also promoting this chemical recycling under the brand of advanced recycling to make it a little bit more friendly. But there is a lot of analysis coming out that they are also not doing a good job in terms of sustainability. So with that, I'm going to come to enzymatic depolymerization, enzymatic recycling. And in a very simple way, vision is enzymes can tackle different enzymes, can tackle different type of plastics at the same environment, therefore making the sorting not required, and bring them back to the monomers, not oil, not polymers, monomers, meaning those monomers can be used to create virgin-like quality plastic again, or they can be used for other material things. For example, there are some companies who are coming up with upcycling, which is, hey, I'm going to use the monomers from plastic and I will create a synthetic vanilla. I'm making this up, which is kind of an upcycling, and then there's maybe more economic value. But right now, as Rhea's factory, we're not getting into that. We are just focusing on, can we take a plastic, use enzymatic recycling, and I will talk about that a little bit more, bring it to monomers. So one more thing though, when we talk about plastic recycling, when I talk about sorting, collecting, usually we, at least at the early days, I always imagine this post-consumer waste. So there's an extra terminology for it. I talked about our home, blah, blah. But there is whole another industry waste source, which is industrial waste. There are some advantages and disadvantages in terms of tackling these two different waste sources. Of course, industrial waste, you think about it this way, I talked to one of these companies, like I am basically Goldfish Campbell, manufacturing goldfish snacks, and I have a manufacturing for my packaging. And of course, my yield in my packaging factory is not 100%. So I have this waste from my manufacturing line, which is just one type of plastic or one type of product packaging material. So that's another source. And then they need to become a one source for our process. Again, I will talk about this maybe later, but like I said, I'm not trying to focus on Rhea's factory, but enzymatic recycling does still require some pre-treatment, but I will tell you it's a little bit much more sustainable and much more friendly. There is here like a very quick comparison. I mentioned about on the right-hand side, mechanical recycling is the most common recycling method used, which is one of the worst recycling or even not recycling. Petrochemical companies coming out with trying to scale chemical recycling, really high temperatures, which means a lot of energy, a lot of greenhouse gas outage, etc. And they are not environmental friendly for sure. And then biorecycling is our focus, because we can do this in a very mild, environmental friendly conditions. I'm going to stop here if you have any questions. Oh, maybe let me push this one too. National Renewable Energy Lab of United States, which is NREL, they did publish this paper, I linked it here, which basically they did look at a virgin plastic, and VTPA here, TPA is one of the monomers of PET. So they use PET because PET has the enzyme most developed in terms of breaking it down. They looked at the PET depolymerization or recycling of PET with enzymes, and they compared that to virgin TPA. Like if I create a TPA with enzymatic recycling versus if we manufacture a TPA from oil, what is the greenhouse gas emission and overall supply chain energy delta? And both of them are in a positive state for enzymatic recycling. And this analysis uses, of course, certain assumptions in terms of how effective the enzymes are. And what we believe is we can improve the productivity and efficiency of these enzymes even further, which will reduce these greenhouse gas emissions and supply chain energies for enzymatic recycling. Yes, please.
So with that, I mean, one of the things you said is it's really, really cheap to make plastic right now through petroleum. And I mean, of course, that'll go up for various reasons around like oil prices and stuff. But if we start having more and more like scope 3 emissions and stuff like that being reported and then taxed and all of that, does that mean that like that's a route for this being more economically viable because like the recycling has 70% lower emissions?
Right on, right on. Like I was gonna get into this too, and I can briefly talk about this. You are right on, because again, I'm gonna get into my pitching mode, but you know, investors like kind of ask us about unit economics, right? And
Yeah.
this analysis that I showed you, part of it, I showed you the greenhouse emission, blah blah. But this techno-economic analysis from NREL, they looked into unit economics too, and they do show that it is expensive right now, more expensive, and I can get into the details why. But it is right now. To your point, there are multiple things happening, right? One is consumer awareness. Two is regulations. Three, brands are also willing to say, hey, I'm gonna have my sustainability goals. So we strongly believe, and I don't have like any perfect estimates, but we strongly believe these unit economics will change. And you brought up another point, really good point, about from a greenhouse emissions perspective and taxes. So yes, short answer is unit economics as of today may not work, but it will change, right? Imagine at one point that I can give you an example, not imagine. This Europe is discussing this new legislation for the last couple of years, to be honest, but they're gonna say, hey, packaging material, 50% of the packaging material should be from recycled material. So there are multiple aspects to regulations, right? Like maybe banning plastic is one of them. Great, we are also in favor of that. But if not, then they will say, hey, you need to use recyclable material. That's great too. That's another area. A lot of companies are working on designing packaging with recyclable materials or coming up biomaterials, which is awesome. And the other part is if you need to use plastic, then you can only use recycled plastic, right? So that is gonna be valuing our output more because of these regulations, even though manufacturing it can be cheaper, which will also change because this enzymatic from a technology perspective, this enzymatic depolymerization is very early. Like it's just started a few years ago. And one good example, if you are really curious, you can look at a company called Carbios, which is a French company. They are building a plastic manufacturing plant in France right now to start piloting PET recycling only with enzymes next year. So you can imagine it's my competitor, but I'm not seeing it as a competitor. I am seeing that company as a leader of this whole industry. And the challenges they are facing is like different ones, and we can get into it. But back to your question, yes, absolutely correct. Unit economics will change for this domain for sure, for different reasons, mainly because consumer awareness, how we understand the plastic problem right now, and we need to have a better solution for that.
And then also, could you click the little hide button on the meet is sharing your screen thing? That's just blocking a couple of the things.
I know, yeah. But now,
Thank you.
computer, hold on, let me try one more time. I heard another bit, by the way, when I'm fixing this.
Yeah, that was Neely. Do you still have that question?
No, I just wanted to get the key under the graph. I got that. Thank you.
Here we go. Okay. All right. So yes.
Wait, can you click that again?
I'm sorry. Oh yeah. Here's the problem. I will do that.
Yeah, perfect.
But here's what it does.
Oh.
Yeah.
We'll go back. I think it should be fine. Just go back to presenting the.
Yeah. I tried. Oh, let me try one more time. Here we go. It's still here. Interesting. Okay,
if you go straight back to the don't change anything on Meet. If you just go back to the presentation, it should be fine.
Yeah, I know. Here we go. You can see what I'm doing, right? It's not like
What? That's so weird.
Yeah.
Okay. Never mind.
Sorry. Feedback to Google Meet.
Maybe you can just drag it to the corner when that height.
Let me try. Sure. Let me try one more time. Any other question, comments? Where am I? Here we go. Can I move it? Is that right? Yeah, here we go. Huh? That's better. but I can also present, which I am here. Okay, here we go. Okay, so which basically, I can skip that, which basically open up that whole regulation, etc. One more part of regulation which we really like, and actually I think it's really important to talk about, is this extended producer responsibility. Because like when I show you this chain here, guys, like it took us a long time, and we are still not there, to understand this value chain in the plastic manufacturing and recycling world. It is archaic, it is fragmented, etc., etc. Because of that same reason, right, it's very difficult to put like, okay, who's responsible, which part, etc. So what the regulations are coming now, and some of it, again, strongly in Europe, some of it at state level in the United States happening too, not at the federal level yet, but that's fine, which is, again, called extended producer responsibility. What the regulation says, hey, company X, if you are manufacturing plastic, you are responsible for the recycling or whatever, right? So just cut to the chase. Hey, you're manufacturing and you're responsible. That is why actually we have been seeing interest from these big plastic manufacturer companies in our startup, in terms of like, hey, what is your technology? What are you trying to do? Because they are aware of this problem and they have resources, which is also a good thing in some way, and they are trying to, you know, improve the situation. Anyway, so yeah, any question here? I remember, I think one topic was around enzymatic recycling and recycling plastic with microbes. So there is a nuanced difference there, which is, you can imagine that I can have a bacteria, a living bacteria, and I can put the bacteria with the plastic, and bacteria literally eats it. That's one method. Our method is slightly different. We produce, or we will produce the enzyme within bacteria, but then the enzyme will be purified from the bacteria. So we will make sure the bacteria spits out the enzyme, which is fascinating, but there are manufacturing capabilities to do that right now, because enzymes are used for detergents and all that stuff. Anyways, and we are using purified enzyme. So it's not a living organism, anything like that. There are advantages and disadvantages of both sides. Of course, I am biased towards enzymatic recycling, but there was a discussion, I think, one chat I had, like, what is it, you know, difference between plastic recycling with microbes, bacteria versus enzymes. So that's kind of the difference. Okay, yes, please.
Hi, Mert.
Yeah.
Two quick questions. One is, how long does it take the bacteria to eat the plastic?
Mm-hmm.
In like hours, days, etc. And then have you also looked into mycelium or fungi as a way to eat the plastic?
Yeah, thank you. Let me answer the second question first. No, we did not look into bacteria approach at all. We are only focusing on enzymatic recycling, meaning we start with the enzyme, we're going to improve the enzyme, we're going to create new enzymes. And when I say enzyme, just imagine I mean, again, a protein, of course, 3D structure, blah, blah, but from a computational perspective, I'm taking it to a little bit different direction, but it's just a sequence of amino acids. And once we have our sequence of amino acids for our own enzyme, we give it to a manufacturing company. They do manufacture in a bacteria, blah, blah. They purify the enzyme, and then they give us back the enzyme purified. So long answer, short answer to your question is, we did not look into bacteria approach at all. It's not our, competency, I would say. But the other question you ask, oh, how long? That's a great question. So when I showed this techno analysis, I don't have the details here on this piece there. They did use certain benchmark numbers. And for example, with the current technology for this enzyme, and it's not the best one in the market right now, but anyways, it's about, let's say, you can achieve about 95 plus of depolymerization within, let's say, 20 to 48 hours. I don't exactly remember the numbers, but that's kind of the ballpark. But those numbers are really critical. Actually, what our company is trying to do, I call those numbers KPIs, right? Like, how long does it take to polymerize how much plastic? What is the temperature? What is the pH? What is the stability of the enzyme, right? The enzyme needs to do its work, let's say 48 hours, and then maybe more, because there will be more plastic put in this process. So the stability of enzyme is also critical. So these are KPIs for us, and our company is saying that we're going to improve these KPIs and come up with our own enzyme that will make this process faster, more stable, etc., etc. I hope I answered your question in a ballpark manner. But which takes me here to cut me off if you have other follow-up questions or new questions. But when my co-founder did this benchmarking lab experiment, we subleased a lab in San Leandro. I was like fascinated by the fact that how simple that was, meaning how clean that was. She basically got the enzyme. We got an enzyme from a university that we will start improving. We put the enzyme in it. We chopped the certain type of plastic, PET right now. We are also focusing on PET. And then we put water in it. And then she also needs to put some buffer to manage the pH, because it works around, I think, pretty neutral, 7 or 8 pH for this enzyme. And increase the temperature chamber to 50 degrees. That's it. And that is the process. I mean, very simplified version of it. But compared to chemical recycling processes I talked to you about, etc., super clean, super mild conditions, which is like the biggest, in our mind, biggest sustainability metric or knob for us. And then I'm gonna show you, this is pretty fresh from our lab pages on lab experiments. On the left-hand side, these are like 2 different punched with paper puncher plastic material, again PET. I didn't put the time here because it took a couple more days than just 48 hours for us, because we were just benchmarking and using different enzymes. But we could clearly see how basically the plastic was gone. Of course, the leftover was in a liquid form in our flask, was the monomers that I just mentioned to you guys. And again, it was just water, the enzyme, and a PET film. And this is, if you are into more chemical stuff, PET, and then when I say monomers, we are talking about this TPA and EG, and just using water. So the other thing, this is our differentiation, but other thing important for the enzymatic recycling is, which is part of our vision, like I mentioned, we have multiple plastics. The really good feature of enzyme, they are selective. And how does that work? Actually is, I'm gonna not do a good job in terms of explaining the science, but as far as I understand, the 3D structure of a protein is like literally a 3D structure with amino acids and residues coming up, etc. And then you can imagine a polymer, right? Another material, which is different. The structure of that material is different for different plastic types. But let's talk about PET and the enzyme. What enzyme does is actually it binds to that plastic polymer, right? It literally locks itself, binds itself to the polymer, and then where it locks, the other amino acids initiates a biocrystal process, which breaks down polymer into monomers. So what I mean by that is, if I put another enzyme to the mix, it's gonna do nothing to this PET. But if there is, let's say, if the second enzyme can specifically bind to another type of polymer, let's say PE, a second type of plastic, and if that plastic is existing in that environment, my second enzyme will now attack or bind to the other polymer, etc., etc. What I'm trying to say is, we can solve this sorting problem or mixed layered plastic problem with an enzyme blend that consists of different enzymes tackling different polymer degrading opportunities, I will say. Yes, please.
So are these all in the same vat? In which case, how do you then like separate the monomers out? Or are you kind of like running them through a chain where different enzymes will pull out different monomers?
If I understand your question, I will flash this one. It's basically how the process works in a little bit more detailed manner. So this one right here is my flask that I showed you. It's basically enzyme blend, water, and plastic comes here. Before that, there's some pre-treatment of the enzyme, like we need to still make them smaller pieces and etc., but nothing super high conditions, etc. And then we get the enzyme. So this is our bioreactor. Your question is about what's happening afterwards. Like I mentioned, water, TPA, and these monomers come out, and then they need to go through a distillation process. And TPA and ethylene glycol may have different distillation processes. Again, I'm not super familiar, but they go through this in-sequence distillation processes. Then we separate TPA from EG, and then we can either, or we will give them to a plastic manufacturer or any other raw material manufacturer if they want to do something about it. And then we also recycle the water to use again. Did I answer your question?
Yeah, thank you.
Okay, and but maybe one layer deeper, your question can be, hey, what if there were more plastic types in this bioreactor? Then yes, that will be a little bit more complicated to distillation process, but that is again post-processing. For example, for PE, which is our second target plastic type that we want to have enzymes to degrade, their output, their monomers are like hydrocarbons, which is a different, different molecules, different monomers than TPA and ethylene glycol. They may need different type of disposals, blah, blah. So maybe the other gist of the question here is this infrastructure doesn't exist yet, to be honest. The Carbios, and there's one more, Samsara in Australia, I think. There are only two that they're trying to build this infrastructure. But again, our vision is this is going to be the infrastructure for plastic recycling in 3 to 5 years. But that was a really good question. Okay, let me come back here. I can briefly talk about, again, like what I am doing in this startup, how we are using machine learning algorithms, etc., which is, you might be more familiar than I am, but it's fascinating to me. Again, like this whole on the left-hand side, enzyme sequence, there are like 3 steps in my mind. One is a chain of amino acids, which is the enzyme sequence. Number 1 is like collection of words. And then they become a 3D structured protein, which is like a paragraph or a text. And then the third one is this 3D structured protein does something specific. It has a function, degrading polymer or carrying oxygen like a hemoglobin or cancer drug, etc., etc. That is the function, which is the meaning of the text. So where I'm getting to that is some universities and actually Facebook also created a foundational protein language model using the exactly similar, very similar transformer architecture that we use right now for LLMs. They use the same architecture. They trained this model with 200 to 300 million protein structures. Not all of them are verified in the nature, but as you guys probably heard about AlphaFold, which disrupted this whole world early on by being able to predict the 3D structure by looking at the sequence. This is the one and the second pieces. Now we had this data set of 300, however many million proteins. So these protein language models are pre-trained with these. So now I have an access, like we do to ChatGPT with API or Gemini with API, whatever. We have an access to these foundational protein language models. So what we are trying to do actually on the computational side, we are saying we are basically building an application specifically to specific for polymer degrading enzyme application on top of a protein language model by using public data. And then, for example, right now we did this a little bit PLM fine tuning. We use publicly available PET data, and then we created new predictive sequences for improved PET, that improved meaning in these KPIs, right? So what I'm trying to say is now we can take that 100, which we will, 100 sequences, we will turn them into real enzymes, test them in the lab, and measure these KPIs, and that will be our private data that will be used for fine-tuning this machine learning algorithm. The second step will be, like I said, we are focusing on PET right now, but after that we will move on to a new enzyme, hopefully for, not hopefully, and for PE, which is the second target. The key there is, currently there is only 1 or 2 enzymes found in the wild, in nature, that can break down PE in a very inconsistent manner. My meta point here is this, actually, by the way, another point. Nature is amazing. We are so much like still learning from nature. Like there's so many efforts in terms of looking at the nature, finding these bacteria or enzymes what they can do so that we can learn from it. Still today, our starting point is what nature did. But in my opinion, it's changing because of this computational power and the models coming up with what they call de novo protein design, which means creating a new enzyme from zero. So it's changing. But long story short, we will tackle another enzyme next, and et cetera, et cetera. And then as we build this application on top of a protein language model, we believe it's going to become stronger and stronger, and eventually we may even have our own foundational model. But that is our computational side of the things. From here on, I can get into more about the Rhea's factories, plan, etc. But I don't need to. We have only 9 minutes anyways. Questions, comments, feedback. I'm all open to your yeah. Please.
And we can talk about this maybe more at dinner if it's not appropriate here. I'd just love to learn more about the sort of beginnings, like when you're going from the 0 to 1 phase for something so deep tech. What was the journey there? And then two, kind of looking ahead, what are your sort of key challenges that you want to like really solve for in the next year or two?
Yeah, I will. Let me stop presenting. For sure, for a dinner conversation, there are multiple challenges in getting into deep tech. Maybe the main one is to be persevere. I mean, every startup needs perseverance, but I think deep tech can easily be pushed back by a lot of different people, be it investors or someone cynical. And they have a point. Hey, this is a long shot. Long shot meaning it's going to take long. We totally believe it's going to work, by the way. So that's one. The second part is, even though we believe it's going to work, technically, it is still much more risky, right? Like if I say, you know what, I'm going to create this software application I have in my mind, I have a certain confidence level that I can do that. There is still a technical risk, right? But now the technical risk even bigger. So again, what my co-founder and I am telling ourselves, like, look, you have this skill set, I have this computational skill set. Yes, it is, probability is lower than what we expect to be in another domain. But if it's going to happen, it's going to happen with combination of those two things. So long story short, the deep tech is hard because you need to really be convinced and want to do this, and it may take longer, and you should be okay for that journey. And we are still struggling with that. Even the benchmark result that I showed you in one slide literally took us like 3 months, which is, we were expecting to do it 1 month. But you know, that's the journey as usual. The second part of your question, next 3 years. So right now, actually, we got a really big milestone. We are raising our pre-seed round, which is a very conservative number, $750,000, and we closed like 60% of it. So we want to close this pre-seed round soon, so that we can look into our execution 1 year. We gave ourselves, 2 of us, 1 year to improve the PET one, so that we have our IP on our enzyme, and we can have a trade secret or whatever, a certain protection for the process. I didn't talk about the process that much, but we can do some things with the process too, not just the enzyme. So in 1 year, we want to get to a point where we have an IP, enzyme, and a process, and the second one is also either there or close to there, which is going to be in the bench lab scale. But once we have those in a year, we can go back to our potential customers and say, hey, we have this now, let's do a pilot project together, because they have the resources, we need them in that sense. That will be from a funding perspective, an opportunity to say, hey, here's the pilot projects we kicked in, now we need a seed round, etc. So that is like in a year aggressive plan again. If you think about 3 years plus, our big vision is we also want to get into the biorecycling plant business eventually. One reason is huge capex and all that stuff, and plans may change. But one positive thing is the fact that there is a biorecycling plant in France doesn't solve the North America problem, because shipping is too expensive, right? Like you cannot ship waste to France, for example. So you need geographically focused solutions. And there are other aspects to that too, like we want to scale up, of course, right? We want to be able to degrade plastic in a very high scale. But also, if you think about municipalities' perspective, and there was one question about like every region is different in terms of sorting, collecting, the capabilities, and all that stuff. One idea, and this is kind of exploration idea, if we can scale the process, but then maybe scale it down, in not from a productivity perspective, but the batch perspective, to have local solutions, right? Like, anyway, so I got into much, but hopefully we want to enable this technology to bring plastic recycling in the most sustainable way in everywhere in the world, basically.
Very exciting. Thank you.
Thank you. That's kind of, yeah, all I had, folks, but happy to hear. Again, not just questions, comments. Yes, decentralization. Let me just read it. Now I can read the chat. It's almost like this model have seen this. Exactly, yes, yes. Actually, we have one. Let me just double click on that one, decentralization. Exactly, we have one. So really the fun part for me, one fun part of the journey is like meeting a lot of different people like this group, right? And maybe I will meet with you guys anyways, even if I didn't do this, but because of Google, but outside of Google, etc. And the spectrum is big. There are like scammers, all the way scammers, which I dealt with. I can tell you guys in the dinner what happened last week. But anyways, all the way to amazing people. One of the amazing people reached out to us. He was really interested. He cannot commit full time, blah blah. But he's really tight. He's really interested in the decentralization idea. So we said, okay, dude, go ahead, do your business analysis. We are supporting you, etc. So that's how we came to this idea, like, and we really liked it. So he's now talking to, I think, a municipality in Arizona who are kind of open about this decentralization idea, blah blah. Long story short, right on. And we are kind of, from a go-to-market strategy perspective, we have one person, not one person, like a quarter of a person consulting and exploring this for on behalf of us. Yeah. And again, it doesn't need to be now. If you're not going to show up to dinner, anything comes across your way, feel free to reach out to Mark or me. I love this topic, and I love being with people like yourself. It's really valuable. That's what I learned after Google. Like, oh my God, we were in such a protected world, and the wild world is crazy. So I value this group and relationship so much. So, Niti, yes, please.
One more question. In terms of like the plastic stream coming in, or some of like, are you like focusing on, hey, bottles are going to be where we get it, or clothing? Is there like the big, what is the big bucket that you want to focus on?
Niti, do you want to join our startup? You're asking me. I can't pay you right now, but hey. Well, amazing question. One couple different things. I'm just gonna scatter a little bit, but textile is a big one. There are competitors getting into textile because it's cleaner stream coming in, and margins are higher. Like maybe you heard the news, Lululemon just had a pants or something that done with the recycled polyethylene or whatever plastic that they use. We kind of steered away from that because it's a little bit crowded for us and etc. But that is one solution. That's one thing you're asking in the right direction. For us, we are planning to start with the post-industrial waste. We don't want to get into the post-consumer waste right now. We can't, to be honest. I mean, I talked a lot about the vision mix, but the first step will be still very simple, right? Like, we still want to integrate ourselves to an existing process and slowly replace it and all that stuff. So short answer is, we are thinking our go-to-market hypothesis right now is post-industrial waste. Maybe one of these plastic packaging material. We're going to go after packaging material for sure. Packaging material manufacturer, we talked about them. And when I say goldfish snack, I'm not making this up. We talk to the manufacturer of packaging of that company. That's why I have that in my mind. So, and they're open, they're curious anyways. So that's our go-to-market strategy. Start small, easy, and then, Evan, please.
Well, I know we're at time, so if this can be in a follow-up on the WhatsApp or something, I'm fine with that. But I'm really curious about, and to John's comment, why not mount this on a boat so it could drive around eating plastic? But ultimately, like even if we recycle plastic and even if it's used in textiles, like I've heard, you wash your recycled plastic pants and the microplastics get in the water stream. Like, do you see a way that bioenzymatic, this kind of process could be used to tackle the microplastics problem? Maybe that's like, several years down the line, but that
Yes.
would be really interesting. And
Yes.
everything has been really fascinating. So thank you for the rest of the talk.
No, I have a couple more minutes. Sorry about folks. Maybe they have a hard stop, but that's a really interesting topic because my co-founder and I have been talking about it. And another question we get is like, hey, are you guys not in favor of plastic ban, right? Like just from it. And we are like, we don't, but it doesn't mean my company will die if we stop plastic right now, manufacturing right now, to your point, because there's so much plastic in the landfill. So we were thinking about even that way. Microplastic recycling can be a little bit different than technology-wise. My co-founder will know more, but definitely if you could collect them at the end of the day, it is still from a material perspective, it is still a polymer, and we can, or maybe, whatever that is, we can still use the enzymatic recycling for sure. Yeah. Very good point. By the way, I love the idea about the boat. John, do you want to push that forward and come up with a one-pager? Isn't that what happens at Google? Like you have an idea, okay, you go do it, and yeah, here we go.
Yeah, sure. I'll put the PRD together.
Exactly.
No, I did see a solar-powered boat that was going around scooping up as a prototype. It sounded pretty cool. Of course, I'm just joking around, really. But there is something there around scooping up plastic that's already there.
Very interesting idea. I agree. I didn't. I'm going to look at the Global Plastic Watch. I don't think I have seen it. No, I don't think I have seen it. Thank you for that too. And again, if anything like this, don't assume I know everything. Ping me. I am still learning. There's so much to learn. Yeah.
Super great
Deep
talk.
sea tech. Exactly. Deep sea, deep beer tech. Love it.
We just need to go like find all the breweries that are going out of business and like.
Exactly. Can I use a bioreactor? different go-to-market strategy. Folks, thank you so much. I know Mark dropped, I think. Thank you. I appreciate it. Again, like, please, if you're interested, Nidhi, let's keep in touch. I can feel you're really interested. I was half joking, happy to check in with you, run my ideas towards you. Like, I love it.
Awesome. I'll see you at dinner tonight. So.
Yeah, see you later.
Okay.
Thank you.
Thanks, Mert.
Thank you, folks.
See you on the what's.
Yeah.